Imagine an AI that can create new materials that are just perfect for a specific purpose. For example, a super efficient battery material for electric vehicles, or a lightweight but super strong alloy for aerospace. Well, this AI can do just that. This has got to be one of the most underrated AI breakthroughs that has come out recently. The possibilities are huge, and this could impact pretty much every industry you can think of. It's called MatterGen by Microsoft, and this AI designs brand new materials from scratch. So in this video, we're going to talk about what exactly is MatterGen, what it can do, and what are some impressive achievements of MatterGen so far. This is quite a technical paper, but don't worry, I'm going to break it down into really simple terms so that anyone can understand. Now, before we cover this paper, let's actually take a step back and look at how we used to design or discover new materials. So going back to really ancient times, I'm talking like early civilizations like Mesopotamia or Egypt, people used basically trial and error to come up with new materials. So they would just mix different substances and observe their properties. Of course, this relies really heavily on experimentation and observation, but we actually came up with some pretty cool stuff from that era. So for example, early civilizations kind of accidentally discovered bronze by combining copper and tin, and this led to stronger tools and weapons. Also, these early civilizations discovered glass by experimenting with sand and heat. Now obviously, this trial and error method is really slow and inefficient, it requires a lot of testing, so you don't really know what you're going to get, and the success rate is super low. Obviously, this is not the best method to use to discover new materials. So fast forward to the early 20th century, we started to see advancements in physics and chemistry, and scientists began using mathematical models to predict how materials would behave before actually making them. In other words, we could use these models to predict how atoms would arrange themselves to form new materials. Now, the advantage of this is it's way more systematic and organized. It reduces any unnecessary experimentation. And this has led to some really cool synthetic materials like semiconductors used in modern electronics, or synthetic plastics like nylon and Teflon. But still, these mathematical models may not always be accurate. It's still really time-consuming, so this brings us to an even better method of designing and discovering new materials. This is called high-throughput experimentation. This basically involves automating experiments to test thousands of material combinations really quickly. And this has led to some pretty cool discoveries, like battery materials for lithium-ion batteries, or solar cells, or new lightweight materials for aircraft, or even new pharmaceuticals. But there are still a lot of problems with this method. First of all, it can still be very slow and inefficient, especially when you're searching for materials with specific properties. Plus, they're often limited by the number of known materials. So it says here, screen-based methods are still fundamentally limited by the number of known materials. The largest explorations of previously unknown crystalline materials are in the orders of 10 to the power of 6 or 7 materials, which is only a tiny fraction of the number of potential stable inorganic compounds. In other words, with these methods, we can only mix and match ingredients that we know about, but it can't create some entirely new material from scratch. And then here it says, moreover, these methods cannot be efficiently steered towards finding materials with target properties. In other words, you're just kind of randomly mixing and matching things together, but you can't really guide the system towards a specific set of goals. For example, design a lightweight yet super strong material for aerospace, or design a material that is really magnetic. It's hard for these systems to design a material with specific target properties. So finally, this brings us to MatterGen. This is an AI that aims to solve the problem of slow and inefficient material discovery. This is a completely new way to design materials directly, and you can specify the desired properties you have in mind. So this is much more intentional, much more targeted compared to the previous method we mentioned, which are not as systematic. So next, let's look at how it works. The really cool part is that MatterGen actually uses a diffusion model. Now, diffusion models are used extensively in the top image and video generators nowadays. And here's a really simple explanation on how diffusion models actually work. So when you use an image generator, for example, and let's say you prompt it to generate a photo of a cat, what actually happens is it starts off with an image of noise like this. And then at each step, it removes some of that noise. And if you repeat this for enough steps, eventually it takes away all the noise and you'll get a clear, realistic image of a cat. Now, of course, the architecture is way more complicated than that, but that's the gist of how a diffusion model works. Now, here's the crazy thing. Instead of getting a diffusion model to generate an image or video from random noise, what if this random noise was actually a random mess of atoms? And then at every step, we take away a bit of that noise until it turns into a more organized, stable structure. Well, that's exactly how MatterGen works. So first, they trained an AI on a ton of stable crystal structures, and at each step, it gradually corrupts or randomizes this structure. So for example, the atom types or their positions or the organization of this crystal would be corrupted. And then after many steps, eventually this structure would be completely corrupted into a random mess. So that's the training process. And then after this AI learns through tons of examples of different materials, you can then reverse this process. So when you get it to generate a certain material, it basically starts with a random jumble of atoms, and at each step it takes away some of this randomness until eventually you get a stable, ordered structure. How insane is that? And note that, like I said, this is exactly how image and video generation works as well, but it was really creative for them to actually apply the same approach but to material design. And here's where it gets even better. You know how for some image generators, you can specify the style or character or composition. So for example, you can use a fine-tuned model to generate Natalie Portman, or another model to create anime line art. Or you can use another model to generate objects made of origami. Well, similarly, you can also fine-tune MatterGen to generate materials with specific properties. This is done using something called adapter modules, which are added to the core model. So here it says we further introduce adapter modules to enable fine-tuning towards any given property constraints with a labeled dataset. This allows you to specify your desired properties like special chemical compositions, or symmetry, or magnetic density, just to name a few examples. So here it says, MatterGen can further be fine-tuned via adapter modules to steer the generation towards materials with desired chemical composition, symmetry, and scalar property constraints. So this includes bulk modulus, which we'll talk about in a second, and also magnetic density. And this feature is the real game changer. Before, with high throughput screening or random search algorithms, you're just kind of mixing everything together and seeing what sticks. You don't really know what you're gonna get. But with MatterGen, everything is much more targeted. You can actually specify the desired properties that you want, and the AI will work towards designing something that actually fits those properties. So this is way more efficient. It's as simple as telling the AI, hey MatterGen, please help me design a material with this magnetic density, and it would actually go ahead and design something that matches your criteria. Plus, remember how I said previous methods were limited by the number of known materials? We can only mix and match these, but we can't really get previous methods to come up with something entirely new. And this is where MatterGen is so powerful. Because this is basically generative AI, it's not just copying what it's seen before. It can take all that info and make something totally new. The same goes for image and video generators, right? You don't just generate existing things. You can get creative and generate things like a pirate ship swirling in a cup of coffee, or an astronaut riding a unicorn in the desert, even though these examples don't exist in real life. So similarly, MatterGen can also get really creative. It's not just limited to the materials or building blocks that we know about. In a nutshell, that's how MatterGen works, but how good is this? So next, let's look at some of its impressive achievements. Here it says, compared to prior generative models, structures produced by MatterGen are more than twice as likely to be novel and stable, and more than 15 times closer to the local energy minimum. After fine-tuning, MatterGen successfully generates stable novel materials with desired chemistry, symmetry, as well as mechanical, electronic, and magnetic properties. So let's go over what this means. First of all, it says MatterGen is more than twice as likely to generate new and stable structures, meaning the materials it designs are more likely to actually exist in the real world. This isn't just some theoretical idea that wouldn't work in real life. And here it says it's more than 15 times closer to the local energy minimum. So the energy minimum of a material is like what's the lowest possible energy required in its resting position, where it can exist with the least amount of stress or strain. So the fact that this is designing something that's 15 times closer to this resting phase compared to other methods means that its designs are way more stable and accurate, which of course leads to better performance in real-world applications. And then here it says we further investigate whether MatterGen can generate a substantial amount of unique and novel materials. We show that in figure 2D that the percentage of unique structures is 100% when generating 1,000 structures and only drops to 86% while generating 1 million structures, while the novelty remains stable around 68%. So this is another incredible sentence. Here's figure 2D, and so it says if you get it to generate 1,000 materials, 100% of these materials are unique. If you get it to generate 1 million, 86% of those structures are unique. That's 860,000 unique ideas. And then 68% of that, so that's like 680,000 of those ideas are novel. So that's pretty insane how this AI model can just come up with so many legit ideas. MatterGen reduces material design time from like years to just days. And imagine if you keep running this, or if you pump more compute into the system, how many more ideas for materials we could have. Or even just out of these, 1 million candidates, I'm sure we can find some way better materials for almost all industries, from automotive, electronics, medicine, energy, etc. I mean, this will have a massive impact on the world. Here's another key sentence. We pre-train a general base model across the periodic table. So unlike earlier models that could only handle a few elements, MatterGen can design materials using almost any element on the periodic table. These are like all the elements that exist in the universe. So this really broadens the range of materials that it can design and discover. Now, so far, I've only given you a high-level overview of the impressive things it can do, but next, let's actually look at some specific examples. So the researchers got MatterGen to design a material with a high bulk modulus value. This is a measure of how resistant it is in being squashed. So the higher the value, the stronger the material is. For example, steel has a bulk modulus of around 160 GPa. Well, here it says we have synthesized a novel material, TACR206, whose structure was generated by MatterGen after conditioning the model on a bulk modulus value of 200 GPa. So basically, they just asked this AI, hey, MatterGen, can you design a material that has a bulk modulus value of 200 GPa? And then MatterGen actually designed it, and the scientists actually made this material in real life and confirmed that it's within the ballpark of this value. Let me tell you about this awesome tool called ChatLLM by our sponsor, Abacus AI. This allows you to use the best AI models out there all in one integrated platform. You can also generate images right from the chatbot, and they're using the best generator out there, Flux Pro. Plus, you can even generate videos with a single prompt. Plus, it has a really cool artifacts feature, so if you're coding or building something with it, it allows you to view and interact with the app side by side. They also have a new coding tool called ChatLLM. This works exactly like VS Code, but it's supercharged with AI. You can chat with an AI on the side to help you generate or edit code, or you can even press tab to autocomplete code. This allows you to code way faster. This is a really powerful way for you to use the best AI models out there all in one platform. Try it out via the link in the description below. So here it says, the actual material that they made in real life had a bulk modulus of 169 against what MatterGen estimated of 200, given as a design specification, with a relative error below 20%. So even though this difference might seem high to you, this is actually very close from an experimental perspective. If similar results can be translated to other domains, it will have a profound impact on the design of batteries, fuel cells, and more. So how insane is that? This is a completely new material that they got MatterGen to design that we've never seen before, and it's as strong as steel. And they verified this in real life and confirmed that it is indeed super strong. Or here's another example. If you get MatterGen to design materials with a bulk modulus above 400 GPa, and for your reference, this is almost as strong as a diamond, which is one of the strongest materials in the world. So this would be ideal for cutting tools or high pressure applications. So if you look at this chart, note that the orange line is a previous method in finding new materials. And then the green line is MatterGen. The x-axis is basically the amount of compute. So you can see as you pump more compute into the system, note that MatterGen can find way more new materials that are as strong as diamonds compared to the previous method. So it found 106 versus only 40, which is more than double what the previous method could find. Here's yet another example. Let's say you need a really strong magnet. This is a super important component for whatever product you're manufacturing. Unfortunately, that magnet is no longer available. It's no longer exported by the country you were trading with. And that was the only country that offers this magnet. Well, there's a thing called the Herfindahl-Hirschman Index, or HHI for short. It basically measures the risk in the supply chain. And as you may know, with an aging workforce, plus with Trump in office, he's going to slap a ton of tariffs on many countries, so this might cause a lot of supply chain shortages worldwide, especially for rare materials. Anyways, a low HHI score means the material is relatively easy to find, so it's less likely going to be impacted by supply chain issues. Well, guess what? You can also ask MatterGen to design a really strong magnet with a low HHI score. So here it says they got MatterGen to find materials with high magnetic density and a low HHI score. So according to the US Department of Justice and the Federal Trade Commission, a material with an HHI score below 1500 is considered to have low supply chain risk. Thus, we ask the model to generate materials with a magnetic density of this, which is really high, and an HHI score of 1250. And for your information, here are some examples of the materials it has created. And these are indeed really strong magnets with a low HHI score. So if you look at this graph here, notice that all these green dots are basically materials that we know about. And then the purple and blue dots are the new ideas generated by MatterGen. Note that most of these have a high magnetic density over here, plus a low HHI score. So notice how MatterGen can produce way more targeted generations for new materials. And with all these new materials with low supply chain risk, then your business will be less likely impacted by supply chain issues. I hope you can see how useful and valuable MatterGen is. I mean, this can have huge impacts across pretty much all industries in the world. Finally, if you compare MatterGen with existing state-of-the-art methods for material discovery, let's look at the chart on the left. First of all, you can see that MatterGen obliterates the competition. So this shows the number of stable, unique, and novel structures, or SUN for short, that were generated by MatterGen versus other methods. And you can see MatterGen by far generated the highest percentage of stable, unique, and novel structures. And then the chart on the right, in a really simple sense, shows the difference between the initial structure generated by each method and the final equilibrium structure. So a lower value means it's much more efficient and accurate. And as you can see, MatterGen had by far the lowest value. So this means it's way more accurate in designing materials. Anyways, that sums up my deep dive into this paper. I'll link to this paper as well as their research blog in the description below. It's quite a technical paper with a lot of complex terms, but I hope I made it easy for you to understand. I find it really fascinating how they were able to take the same approach from image and video generation and apply this to material generation as well. And heck, this is going to be the worst material generator we're going to get. I think in the coming years, we're going to see a lot more new and efficient materials, and it's going to revolutionize the things we use in everyday life. From our cell phones to appliances to medicine, everything is going to be way more productive and energy efficient. It's exciting times ahead, so buckle up and try not to die. Anyways, let me know in the comments what you think of all of this. As always, I will be on the lookout for the top AI news and tools to share with you. So if you enjoyed this video, remember to like, share, subscribe, and stay tuned for more content. Also, there's just so much happening in the world of AI every week. I can't possibly cover everything on my YouTube channel. So to really stay up to date with all that's going on in AI, be sure to subscribe to my free weekly newsletter. The link to that will be in the description below. Thanks for watching, and I'll see you in the next one.